So, in context to the polymers, there is a unique thing with the polymers about their molecular weight distribution. So, that idea I will be explaining now. So, let me start a new canvas. Okay. So, what are we going to discuss is the distribution. So, distribution of the molecular weight of polymers. So what happens here is, unlike, let's say, any physical chemistry concept where you might have seen that if I have a stoichiometric molecule, let's say a simplest molecule will be hydrogen, or we can take CO2 or any mostly inorganic compounds also, but let's not get confused with the organic things. So let us stick to inorganic compounds. You usually have one molecule, and this molecule will have a fixed molecular weight. But in polymers, it is not a stoichiometry of two atoms or n number of atoms who are going to be fixed together. It depends upon the degree of polymerization. So let's say if you have ethylene, then you can have 100 number of molecules attached to one molecule, or you can have any number of molecules attached to it. You can have cross-linking and so on. You can have branching, you can have cross-linking, and different things can happen. So here it depends upon the degree of the polymerization, that how much molecular weight you have. Also, it depends upon the cross-linking, branching, etc. So now we understand that. So let us say that I am making a polymer of this mer. Okay, this single molecule, I am making a polymerization. I'm doing a polymerization of that. So if I'm doing that, then it depends upon my processing route that how many chains will I be making. So I might make one chain, that will be a laboratory processing, and in reality I will be making many chains which will be looped or tightly looped or in the form of cilia. So this is a tight loop. This is a cilia, and usually there are a lot of Latin jargons in the science and technology field, and we should be fortunate that we are not in medicine, because there you will have a lot of Latin influence. So this is just the name of the shape, and so there can be different type of structures in polymer, and there will be different chains. These chains might be of different lengths. So you can have a short chain, you can have a longer chain, you can have a much longer chain, or so all types of distributions might be there. Therefore, there is not a unique molecular weight which can be assigned to this whole polymer which you have made. So what can we do? We can do a few things. So basically, first way of calculating molecular weight of a polymer is to find out how many number of molecules are there. Okay, so let us say that I have n number of mers in certain system. So I have 4 number of molecules in some system. I can in some chains I have 5 number of molecules in some chains. So let us say I have a few chains here for whom I have different amount of weights associated with it, because it will depend upon how many number of of mers are there. So let us say I have one number of chain which has 10 number of mers in it. So the mass of that will be 10 into mass of one, let's say it is ethylene. Sorry. So let us say it is ethylene. So the molecular weight of one ethylene, let us write as METH. So the mass of that chain will be 10 into METH. I can have another chain and the number of that chains is, let's say, 5. So I have 5 number of chains where I have in each chain I have let's say 6 number of ethylene molecules. So I have 6 in each, and then I have 5 chains, and so this will be the mass of that. Similarly, I can have 100 number of chains where I have 3 mers in each. So 3 into 100 into methylene will be the molecular weight of that. Okay. So I do this. I first do the counting and then I multiply each number of chain. So actually, what I have done is this is actually n into m, because I have already multiplied n here. Okay. So in order to make it a little clear, let me do something. So m is, let's say in this particular chain, which I have one only, I have 10 number of molecules in it. Okay. So 10 into METH is the mass of that chain. And how many number of chains do I have? 1. Then I have 5 number of chains where I have 6. Let's not get confused. So 6 number of molecules are there. So 6 into METH is the mass of one chain. Okay. Then I have 100 number of chains of such type that I have 3 number of mers in it. So the mass of those short chains are 3 into this. So then I can do the multiplication and I can find out that what mass is being contributed from which size of chain. So for the first one, I will have 10 into METH into 1. For the second one, I will have 6 into METH is the mass of one chain multiplied by the number of chain, and then 3 into METH into number of chains, which is 100. And then I sum all this. So NiMi will be the total mass I have in the system, right? So this is the total mass, and the molecular weight average of this I can calculate by summation of NiMi divided by total number of chains I have. So summation of Ni. So this is my number average molecular weight. Okay. So this is called number average molecular weight. Okay. And so this is one type of calculation which I can do. Apart from that, what I can do is, so I can find out the weight average. So weight average molecular weight. Okay. So just a second, share the screen. Where is, yeah, here. So in number average, what we did was we have number of chains, we have mass of each chain, and then we calculate Ni into Mi, and this part is very clear, and then we take this kind of average. In weight average molecular weight, what we do is we have Ni, that is clear. Then we have Ni into Mi, That is also, you know how to do that from here. And then we calculate something we call weight fraction, Wi. So I have one number of chain with a mass of how much was it? This was 10. So I will just write small m for METH. Then I have 5 and 100 and 6 and 3. There are 5 number of chain, 100 number of chain, 6m and 3m. Okay. So now how do I calculate Wi? Wi will be NI-MI. So this I can calculate as NI-MI divided by summation of NI-MI. So what am I doing here? I'm dividing each chain's contribution with the total mass of the system. So that is what I call weight fraction. So this will be, let's say, so what is the summation of NI-MI here? I have 19m. Okay. I think this is MI. Sorry. Yeah, this is just MI. So NI-MI will be 10m. This will be 5 into 6. So 30m. And this will be 300m. Okay. So the summation of NI-MI is 340m. And then I have to calculate weight fraction, which is NI-MI divided by summation of NI-MI. So that will be how much? So for the first one, it will be 10m divided by 340m. Okay. For the second one, it will be 30 and mm will get cancelled. So 30 divided by 340. And for third one, it will be 300 divided by 340. Okay. And from Wi, I calculate the fraction, which is Wi into Mi. Okay. So then this fraction multiplied by that. So 10 into this is 10 divided by 340. And then for this, it will be 30 into 6 divided by 340. And then 3, there will be an m here. And then 3m into 300 divided by 340. So this is my Wi-Mi, so weight contribution from each chain, and then I can take weight average molecular weight of the system as summation of Wi-Mi divided by Wi. So no, so the total weight is NI-MI. So sorry. So the total weight is NI-MI. So this will be my weight average molecular weight. Okay. So this is showing how much mass is being contributed from. So let us go a little deeper in this, what is happening. So I have 3 number of shorter chains, then I have 4 number of, or let's say 5 number of longer chains, and then I have 1 very large chain. Okay. So the weight of this might be larger than this. Okay. So if I am taking a number average of, so number average molecular weight, then that will be showing that how much contribution is coming from those chains which are larger in numbers. Okay. So that will be shown by this. And the molecular weight, which is the average of the weight, that will be showing the contribution from those chains which are heavier. Okay. So this will be showing the contribution from heavier chains. This will be showing the contribution of more number of chains. More number of chains. Okay. So both of these do not uniquely define the polymer property, but a combination of these two is called molecular weight distribution, which is the ratio of the molecular number weight average and molecular weight average molecular, and this is called molecular weight distribution. Also it is called poly dispersity index. Okay, and this has great effect on the mechanical property of the polymers. So we will discuss in detail about this later on, but at this point of time, this concept should be clear to you, that how can we define the molecular weight distribution of the polymer by number average molecular weight and weight average molecular weight, and what is the essence of these two, and what is molecular weight distribution and poly dispersity index. Okay. We do not have this. So this formula is simply the summation of, because we already are taking fraction here in defining Wi, so we don't need to do a fraction anymore. So just the summation of Wi into Mi will be the weight average molecular weight of the polymer, and the poly dispersity index is actually opposite of what I have defined. So this is the weight average divided by the number average. Okay, so this is weight average molecular weight divided by number average molecular weight. Okay, so this is that. So today we will start with the mechanics of polymers, and before we have learned about the mechanics of metallic materials, but whatever we studied, let's say for example elastic property of metallic materials, plastic property of metallic materials, and creep and impact, and what is the effect of the velocity of deformation you apply on the system, and all those things we studied with the major perspective on the metallic kind of material. So what we dealt with so far in previous courses, as long as the mechanics of materials was concerned, we dealt with the idea that we had simple crystalline materials. We did not deal a lot with how the deformation happens in amorphous materials, and but application wise there are many other types of materials where the complete mechanism of the deformation is different. So we dealt with metallic materials, and that for sure comprises of most things we see in the society and in our households and in the daily life applications. But nonetheless, we do have other material types also which we see on a daily basis. And in the recent years, you will realize that a major contribution has come from polymers, especially plastics. You will see a lot in your daily lives. And because if you just see how much waste or garbage you have to throw out every day, you will see 90% of that is plastic. But that is not that. So it's not just the negative part of it. There are, so you see why plastic is being used so much. The reason is this material is so much unique, so much different for its applicability, that it has found its place by replacing steel, metallic materials, by replacing, it has got applications in bio things, it has got applications in utensils, it has got so it has replaced also ceramics, so clay cups and all those things. You have plastic bottles, And if you look around yourself, you will see most things are made up of polymers. So you have PVC doors, you have frames of a glass window which are polymers, you have tables, you have mats, polymers, you have tire, you have body of a box, you have the mobile phone cover, and the whole mobile phone, there is a lot of plastic in there. My specs frame can be polymer. I can have a pen whose body is made up of polymer. So this thing has replaced the metals to a larger extent because this has a lot of properties. So for example, if you do not want to make let's say a table of a metallic material, because first it will be heavy, and second it will be cold in winter and it will be very hot in summer if you keep it open to the daylight in summer. So those properties also, the formability of plastic is different, the processing is not so it's not so expensive, and it's cheap, it's lightweight, and there are these things which make it possible for polymers to replace a lot of things. So biomaterials have unique properties, but biomaterials, the synthesis of biomaterials is not so easy as making polymer is. And so replacing polymers from the society is a huge concern, but it is also, in my opinion, not possible. So the better way would be to make a polymer which is environmental friendly. So that is the societal discussion on polymers. Now let us come back to our topic. So when we say polymer, I have a simple toy with me with which, you know, the kids, they play, but I'm using it to show you a demonstration. So imagine this special shape thing, which is also made up of plastic, is a mer. So imagine this to be a hydrocarbon molecule. So you can imagine the center to be carbon, and you can imagine rest to be hydrogen, although there should be only 4 hydrogen, but here there are more. So take it just an example. So you have a big atom at the center, right? So it's a hypothetical hydro something. So you have a big atom at the center, and then you have the hydrogen atoms. And what you can do is you can join them. So this is one molecule, and I can join these two. So this is another one which has a different color, but it's the same thing. So I can join these two in this way, so that you see the center atoms are making a special bond with each other, right? And rest of the things are same. So this is again different from what will happen in reality, because if two molecules are uniting, they will have to lose one bond. But in this example, you can just ignore that part and understand that that has to be true. So I can keep on adding these, and I will be making a big chain of this, right? And you see how this is completely different from a metallic material. So I can keep on adding, and this will keep on elongating, and I will have a very, very large chain of many mers. So that will become polymer. Okay. So what can happen is, so first of all, we need to understand that this thing has covalent bond in it, unlike metallic materials where you have metallic bonds. And these covalent bonds, in comparison to metallic bonds, are very, very strong. So breaking these are not easy in comparison to breaking the metallic bonds, or moving them. So that is one difference. And apart from that, you don't see a cubic kind of crystal formation here, but you can have an ordering in the system. So how can we have an ordering? So before that, we need to understand something, that when we make polymers, we are not making a single chain. We are making many chains which will be living together. So imagine this to be one chain, and then I make another chain, let's say is this. So I have two chains, and these two chains can be like this. Yeah, it can be looped around, but if they are like this, if they are just lying next to each other, so if they are lying next to each other, there is a force between these two chains. But this force is this force which you cannot call a bond, but it attracts these two chains together, is not a covalent bond, but it is a van der Waals force. And this van der Waals force is very weak force. So when I apply load on the system, when I apply force on the system, what can happen is that these two chains can move along each other because the force between them is very weak. Okay, but something like breaking this thing cannot happen because of the load application, because that will take a large amount of load. What else can happen is that this mer can keep on elongating in this way, and it can become longer and longer. But more easier would be that they somehow unite themselves. So what I can do is I can put it like this, and that you see I cannot rotate it in one go, but sorry, so it's like this, and then I just keep it there, and you see I have given it a direction, but I can also give it a direction like this. So you see these two chains have folded on each other in a very easy way, and this can go on. So this can make a loop. So now I will try to demonstrate the same thing using schematics. So let me share the screen with you. So as I said, I can have a very large chain of each mer. So it will be something like this. And so I will be drawing just a line in order to present a longer chain. And this chain can fold itself in a way so that it forms an order. So it can fold like this, and it can keep on doing that, and it can come very close to each other, but still between these two chains there will be van der Waals force, and here in each mer you have covalent bond, and that is a stronger bond in comparison to this one, and that's why movement along between the spaces of two chains is possible, and it is very easy. But making this kind of foldings throughout the body of the polymer is not energetically favorable. So what will happen is that polymer usually are folded like this in a short range period, and then they just randomly are going, and then they can fold again locally, and they can fold like this. They can make a small region, okay, of ordered folding, and then they can loop around like this, and they can make another folded structure somewhere else. Okay, so these structures which are folded, which are in order, they are called crystallites. Okay, so they are the crystallites. So they are the ordered structure in the whole polymer. Okay, so the whole polymer is not completely folded, is not completely in order. So this part of the polymer is amorphous. So this part of the material is amorphous. Okay, and the others are crystallites. So what you see is that polymer basically is a combination of ordered, short range ordered, and amorphous type of material. And this is very similar to what we had in the metallic materials also. So in the metallic materials also we had regions where the things were crystalline and regions where the things were amorphous. So if I take a small microstructure of a metallic material, I usually have a lot of grains in it, right? So these are the grains, and in each grain, the crystals are oriented in certain directions, right? So crystals are oriented in this direction, and then in crystal here, the crystals are oriented in this direction, and this part, sorry, and this part here is the part where you do not have any type of ordering. So they don't have orientation of this grain or this grain here. Okay, so this is the reason of discontinuity between grain number 1 and grain number 2. Okay, and that part which we call grain boundary is the amorphous part of the material in the metallic material. Okay, and this part is the crystalline part. So basically in metals also we have crystalline and amorphous, but the spatial or volumetric contribution which comes from amorphous part is very less, lower in comparison to the crystalline part. But in polymers, a huge contribution comes from the amorphous part of the system. Apart from that, crystallinity in polymer, as you have seen in here, that it is different from what we have in metals. So in metals, you have ordering like this. So you have crystals which are in this order. So you have unit cells which you can keep on repeating in 3 directions, and that is how the crystalline formation will happen in metallic materials. In polymers, you will have folded structure of the molecular chain. Okay, so that is the basic difference in the structure. So because of the nature of how polymer is, so if I take let's say ethylene, or I can take I can take ethylene. So I will have carbon, carbon, hydrogen, 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 and then these two. So that would have been a double bond here, but because if I'm polymerizing it, so another molecule of ethylene will be added here. Okay, so then I will have carbon, carbon, hydrogen, 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 hydrogen here. Okay, and so on. So I will have many molecules added together, and this will make a molecular chain of polyethylene. But this, although looks in 2 dimensions, too easy to draw and easy to understand, but the real structure is not so. The real structure can be in 3 dimensions, and because of that, as I showed you in the example of that plastic toy, what happens is that there is something called a steric hindrance. So this carbon will be like that, and then you have hydrogen which will be at a certain angle. Okay, so So because of that angle, it will be a three-dimensional structure. So let us say that this is my carbon atom, and then I have another carbon atom, and then I have, let's say, so here I put hydrogen here also, and at the end also I put hydrogen. Okay, so this carbon is attached to 3 hydrogen atoms. So I have hydrogen here, I have hydrogen here, I have hydrogen there, and these 3, let's say, are making same angle from each other to have potential energy minimum. So this angle will be 120 degrees, right? And this angle also will be 120 degrees, and this will also be 120 degrees. So they are separated in 120 degrees, and you see it is a structure in 3 dimensions, right? So this is, let's say, my x3 axis, this is x1, and that is x2. So again, this atom will also have hydrogen at the, it can be again at the space of 120 degrees, but these 2 atoms with hydrogen at 120 degrees can have a rotation also. So let me have that schematic in a more clear way, let's say. So this is my first carbon atom, and here I have a hydrogen atom. So I will draw the hydrogen atom with this color, okay? And then I have another hydrogen here, another hydrogen there. So this is another hydrogen, that is another hydrogen, okay? And then I have another carbon. So that should be blue. And now, so if I'm looking, so if this axis is, let's say, x1 axis, okay? So that is my x1 axis, and this is my x2 axis, and this is my x3 axis. And now try to look from the plane of x2, x3, okay? So from the plane of x2, x3 in x1 direction, if we try to look, then it may look like this. So I have carbon, hydrogen, hydrogen, and this is my first atom, and the second atom might have the same orientation of hydrogen, or it can be different, okay? So it can simply overlap if I'm looking from x2, x3 plane, okay? So it can simply overlap on this. So you will not be able to see the second atom, which is just behind this, or it can have rotation, okay? And the behind one can be somewhere here, okay? And then 120 degree somewhere there, and 120 degree somewhere there, okay? So it can have a rotation, and then the third one can overlap on first one. So you see, this is something like what we have in metallic materials for the stacking, okay? So although we will not have stacking faults, there might be faults, but those are not called stacking faults. But this is something similar to what we had in metallic materials, ABC kind of stacking. We have similar thing because of the rotation of the chains. So this depends on what? This depends upon that hydrogen and hydrogen atom will, how much do they like each other, or how much space they need. So you see, hydrogen is a small atom, and this doesn't need much space for the 2 hydrogen atom to be closer to each other, right? And the angle which is coming, a constraint in the structure is that they have to be at 120 degrees from each other. So these are the structural requirements which the molecule will have to have in order to form the structure, right? So that is what is going to be, but the scenario might change as soon as instead of having hydrogen, you have a chlorine, let's say. Okay, so then it will become polyvinyl chloride. So if you have chlorine atom size is different, so his demands are different, and because of that you might have, so here you will have 120 120 120, but there you have 2 hydrogens and 1 chlorine, so there you will have to have a different angle. Okay, and because of that you will have to change the angle. So these two probably will contract, so 2 hydrogen atoms will have to come closer to each other, and chlorine will be taking more space because the size of that atom is larger. So this steric hindrance, which is the hindrance or the necessity because of the size of the atom, can cause this steric hindrance, and that contributes to the mechanical response of the material. Apart from steric hindrance, apart from this, we can have a contribution because of the structure of the system. So there can be 3 types of structural formation in the polymer chains. One can be that we have a random distribution of the surrounding atoms. So random distribution we can have, and that is called atactic. So in this case, let us say if we have polyethylene, so we will have we can have polypropylene, so then we will have CH3 here, okay, and hydrogen, another hydrogen here, and here then just out of randomness I can have next CH3 there, and then I can have CH3 maybe not here also, maybe here. Okay, so where this CH3 will be is not following any kind of rule. It is just purely because of randomness, and this kind of distribution is called atactic. Okay, the other possibility what we can have is isotactic. So in isotactic, it is not completely random. Instead, you will have alternate layering of, all the one type of side molecules will be oriented on the same side. So that will be isotactic. So here CH3, then H, and then CH3 again here, and CH3 again here, and so on. So this is the second possibility which we can have, and third possibility can be, which is called Syndiotactic. So in Syndiotactic we will have alternate layering. So I will have CH3 here, I will have hydrogen here, and then I will have CH3 here, hydrogen here, CH3 there, hydrogen there, and so on. So you see, in the first molecule, in the first mer, you have CH3 on the upper side, and in the second one it's on the lower side, third one it's on the upper side. So this is another pattern which is being followed, and it is alternate. So this is called Syndiotactic. So these 3 possibility exists, and because of, so what so far we gathered is that the mechanical response depends upon the amount of crystallinity we have in the system. Okay, the second trick is the chain structure. So the angular hindrance, and so chain structure basically can be divided into 2 groups usually. So cross-linked chains and single chains. So not linked, unlinked. Okay, so cross-linked would be that if I have, let's say, let me show you this demonstration again. So cross-linked will be something like this. So sorry, So you see this is cross-linked. Okay, so instead of van der Waals force, you have a bond here which is joining the two chains. So this will be a structure where there will be, so the movement of these two chains is not easy because you have a covalent bond which is joining these two. So that is a cross-linked structure. And the other one which is unlinked was simply what I showed previously. There will be no cross-linking. So in those cases, we will have, so that is the chain structure. And third, you can have the type of distribution. So what we talked about, atactic and iso and syndiotactic. Okay, so these molecular contributions are there to describe how the mechanical response is. If we look at the mechanical response of polymers, then what we saw in the metallic material, so let us draw a stress strain diagram of a metallic material. So in order to do that, let me draw a stress strain diagram of a metallic material. So and then I will be drawing the polymer also on the same graph. So let me make two. Okay, so this is stress and this is strain, and let me choose green for polymer, stress and strain. So in metallic materials, what happens is that we have linear elastic part, and which follows, so the linear elastic part is Hooke's law. So that goes like this. And in the polymer also I will have, so I'll just draw it here so that we don't have to bring it. Okay, so in the metallic material we will have the linear elastic part which follows Hooke's law. Okay, so sigma is equal to elastic modulus into epsilon, so this follows Hooke's law. Then you have strain hardening. So this region is strain hardening. So strain hardening is happening because dislocations are multiplying with each other, creating more dislocations, and the intersecting dislocations are also offering resistance to further dislocation, right? So this is my yield strength. This is my ultimate tensile strength, and then I have damage in the system which is causing the material to degrade, and at certain point I will have failure of the system. Okay, so this is how a metallic material looks like. Just a strain diagram of that. In the polymer, unlike what we had here in metals, the elastic modulus is very smaller in comparison to metallic materials, and it is actually very, very small in comparison. So the metallic materials usually are in the range of 200 gigapascals or something. Here you will say it could be 5 megapascals, 20 megapascals or so. So that is a huge difference. So in polymers you can have linear elastic part, then you can have breaking of crystallite parts. So you remember there were folds in the system, and these folds are the crystalline part. And what is happening when you apply load on the system, so there is an amorphous part and then there is a crystallite part, and I'm applying force on the system. So what will be happening is that this folded structure will open up slowly, and because once it opens up, it takes more space, so your strain is increasing, right? So because of the force application, there has been a delta L by opening up of the crystalline, and once all the crystallines has opened up, they will align themselves. So let us say we had 4 folded structure next to each other. Okay, and these 4 folded crystal structures will open up like this, and then they have opened up, and then they will align themselves in the direction of the force applied. Okay, and once they are perfectly aligned, then if you increase the load further, each fiber, each chain will break. Okay, so let's say there are 4 chains, 1 chain breaks, 2 chains break, then the same amount of force is now much higher on the remaining 2 fibers, so they will easily break. Okay, but breaking a single chain, so breaking that is a breaking covalent bond, that takes a lot of energy, and a lot of energy is taken in opening up these crystallites and aligning them along the strain direction. That takes a huge part of the deformation. Okay, so let me stick to the stress strain diagram. So here what happens is that crystallites are breaking, and that offers some resistance, and then once they have opened up, there is a little softening, and all of them have aligned together, and now you have to break each chain, and for that you need a very high stress, and then there's a failure. So something like this we saw on the mechanical testing behavior lab, where we tested one polymer. What was happening to the specimen was that this specimen was like this, and then after a lot of deformation, the specimen simply was flat elongating like this. Okay, there was no nicking, nothing like that. There was a change of color, of course, and that we will discuss later on. And what you might go back to the video and see in the, I think in the red sample which we tested, there you might have seen a small crack, micro crack, you will see. So probably what happened, that few fiber broke in the middle somewhere, and then it broke suddenly. The other observation which you might have seen is that as soon as they broke, the color came back to the original color, and the broken sample, if you put them together, they actually had the same dimension, almost the same dimension of what we started with initially. So it looked like the whole strain recovered after the deformation. So in polymers, what can happen is that the elastic deformation may or may not be linear. Okay, so what can happen is that if you unload it, the whole strain will actually go back. So the stress strain curve will follow the same path while going back, and the total strain can be 0. It will, although, take some time. It will not be instantaneously 0. It will take some time, and it will be 0. Sometimes you can have a plastic or a permanent strain, as we have in the metal. Okay, so we can have that also. So we can have a non-linear kind of elasticity in polymers, and we can have an elasticity which is time dependent. So we will discuss about how and why there is a time dependence in polymers deformation, and how can we understand that in easy terms. Okay, and this kind of deformation is similar to creep deformation in metals, but also not very equal to creep deformation, because creep is a permanent deformation. You can have a recoverable or reversible time dependent deformation in polymers, as well as you can have permanent time dependent deformation. Okay, so in the polymer technical terms, we call it viscoelastic and viscoplastic. Okay, so we will deal with these things and why these things happen, why there is a rate dependence or time dependence in polymers. We will discuss that in the next lecture. So that is all for today, and thank you very much.